Hello everyone. So in 5 minutes we'll be starting our session. So those who are connecting with us through Google Meet and through YouTube, I will request you all to connect soon because in 5 minutes we'll be starting our session today. Thank you. Those who are watching me on YouTube, please do let me know if I'm audible properly. Good morning, Junaid. Those who have joined us through YouTube and Google Meet, please do let me know if I am audible properly. Okay, fine. So let us wait for other participants to join, Junaid. So within 5 minutes, we'll be starting our session. I hope all of will be joining within 5 minutes. Let's see. So we are waiting for others to join. In 5 minutes, we'll be starting our session. And we are already live on YouTube also. So those who are joining through YouTube, you can connect us as early as possible. Yeah, today's topic is modal analysis for the practicing engineers. Okay, so the topic that we'll be covering today, it's modal analysis for uh, practicing engineers, how it will be helpful for you. So on that we'll be talking, we'll see what are the fundamentals of it and how we can use it in our daily practice. Yes. Yeah, I will show the fundamentals actually. How we can do that, I will show that. So I think we can begin our session because it's already 11 and people have joined in our YouTube platform also. So I guess it is better to begin. In between, whoever is coming, they can join easily, right? So let me share my screen to all of you. Please do let me know if the screen is visible. Do let me know in the chat if the screen is visible, everyone. Okay, fine. So as usual, first of all, we'll be understanding the fundamental concept of the topic that we are going to cover today, which is modal analysis. So this modal analysis is not only used in the field of civil or structural engineering, it is also being used in the you can say mechanical engineering, to the aeronautical engineering, those who are making cars, that means the automobile engineers. So this modal analysis, it's not a process to a specific engineering stream. It is a in general term which is used, you can say, vastly in every single core field. Okay. So basically the modal analysis is nothing but the fundamental behavior of a you can say any object which is under loading, okay, or which is under vibration. So today we will be talking about in with respect to our field, which is civil structural engineering, how we can use it and what are the aspects that we need to understand of it, right? So first of all, let us take a very single or simple frame like this. Okay, so it is a very simple frame we have. So the total mass, suppose this frame has total mass which is m1. Okay, so now how we idealize this particular structure, how we are going to idealize this particular structure. So it is a 2D frame. Suppose it is in x and z axis, the horizontal axis is x and the vertical axis is z. Okay, so how many degrees of freedom this particular mass has, if you can tell me, or this frame has? How many degrees of freedom this particular frame has? Can you tell me? Yeah, so it can move in this direction. You may say that it can move also in the vertical direction also, if you have the vertical acceleration. That is a different topic. Okay, that is a different topic. In general, if you say that this particular frame can move or can translate along the direction of x, so we can idealize this as a single degree of freedom system. So this is a m1 mass, this is y, and suppose we have this some stiffness here, and it can translate along x direction in both the directions. Now if you provide or if you give any initial excitation to this particular structure, Okay, suppose because as per Newton's law, if the structure is in rest, obviously it will be always in rest unless or until we give any you can say external force on it, right? So to make it in you can say to move it once, right? So what you have to provide, you have to give a initial excitement to the structure. So suppose we have given an initial excitement to the structure in terms of the frequency. Suppose like this, we have a frequency and we have you can say assign this to the structure here, to this particular frame here. Or let's not talk about all this frequency and all, let's not make it complex. We have just given a push to this structure, suppose P. Okay, just give me 1 second. Hello, sorry, actually I had to go for some important work actually. Okay, so what we were discussing that uh, just 1 second. So this frame you see here, it has 1 degree of freedom, so we call it as single degree of freedom system, right? So now if we give an initial excitation or initial force to this structure, so this structure will, or this you can say frame will start moving. And how it will be moving? So it will be moving like this. This to and fro. Once it will go in this direction and again it will come to this direction. Right? Okay, so we will get a displaced shape which is something like this. If we idealize this as a single, yes, anyone is telling anything? If you have a question, you can ask me. Hello? Okay, so here it will move in such a manner.
No audio, sir.
No audio. Oh, okay, sorry. Is it audible now?
Yes, sir.
Okay, sorry. So what I was saying, that if we give an initial excitation to the frame, and as we are idealizing it as a single degree of freedom system, so what will happen, that we will have this kind of behavior here, that the structure will displace in this direction, and again it will move to and fro, right? Now let us take a frame where we have different masses and different levels. So suppose we have a frame like this, and we have now we have 3 floors. So here we have mass 1, here we have mass 2, here we have mass 3. Fine. So now how we can idealize it? So if you see here, it will be something like this. Mass 1. Suppose I'm just not drawing those stiffness here. It is there, just M2. Let me draw it, otherwise you may get into confusion. And M3. So stiffness 1, 2 and 3. These are the story stiffness. Okay, and this mass, where we are considering that the mass of the whole particular story, is, you can say, concentrated. This is nothing but the lumped mass. Okay, this is nothing but the lumped mass that we are considering. Lumped mass. So it is nothing but the point where we assume that the whole mass of the story is concentrated. Okay, so why we consider this at the floor level? Why not here? Why not in between? Because if you see, at the floor level, we have the slabs, we have the beams, we have the slabs. So the more mass or more rigidity is, if you see, we will find at the floor level itself. If you compare with the whole story, we will have higher amount of mass at the floor level itself. So that's why we consider that the total mass of the story is being concentrated at this particular position, at a point, and this is nothing but the center of mass for this particular story, right? So now the similar thing we have done for other stories also. Now let us consider this every single story as a single degree of freedom system. Okay, so we have one single degree of freedom system here, we have another single degree of freedom system here, we have another single degree of freedom system here, because these masses are allowed to move individually in this particular plane, which is my XZ plane, right? So that's why, as we have multiple single degree of freedom systems where these masses are allowed to move freely, or you can say allowed to translate independently, so these systems are called as multi-degree of freedom system. Why multi-degree of freedom system? Because suppose this mass is moving in this direction, the other mass is allowed to move in this direction, the other mass is allowed to move in this direction. Okay, so every single story has their own degree of freedom. Okay, that's why we call it as multi-degree of freedom system. So now, what is the expected behavior of a multi-degree of freedom system? Okay, so let me draw it again here. See, I will not go for solving those matrices, solving those eigenvectors, Ridge vectors here. Okay, I'm just giving you an insight of this particular concept. To understand the dynamics behind it, the mathematical formulation behind it, you can always refer the books. There are very great books available, like Dr. Anil K. Chopra. This is very famous, all of you know, for structural dynamics. So you can always have a look on it for the better understanding of the mathematical formulation. Okay, so now if I again write it M1, M2, and M3. Okay, and we have given some initial excitation to the structure. So what will happen? What we expect, that the structure will displace like this. Right? Okay, this is one behavior that we can expect. So I'll write, suppose step 1. Okay, and we are getting this displacements at the different story levels. Okay, so if we consider this as direction 1 and this as direction 2, and if we consider this as story 1, story 2 and story 3, so how we can write these displacement shapes or the displacement values? Suppose this is the phi story 1 along direction 1. Okay, we can write this. Let me draw it in magenta color only, it will be better, I guess. Yeah, so it is phi story 1 direction 1, it is phi story 2 direction 1, it is phi story 3 direction 1. Right, we can define these things like this. Like I have given phi, you can give any symbol to this. Okay, now what is the next expected behavior? I'm drawing the ideal behavior of this particular frame, a multi-degree of freedom system here. So again we have M1, M2 and M3. So we had the displacement like this already. Right, now what is the expected behavior? Now these two stories or these two masses can move in the other direction, like it will be a to and fro movement. So these two masses, suppose we are considering that this mass it is not displaced from this position that we have got here, but the other two masses are displacing. So it can be like this. As we have already said that these masses are allowed to move individually, so we can have a displaced shape like this. So here it is phi 1 1, here it is phi 2, now in the direction of 2, here it is phi 3 in the direction of 2. Right, now let us see again. Another behavior. See, we have seen the individual movement of all the three stories. We have seen the individual movement of now 2 and 3 stories. Now again, if we break it more, M1, M2, M3. So now it can be of this shape. Here this is my phi 1 1, this is my phi 2 2, this is my phi 3 1. Right, right or wrong? So now as you are seeing that we have got the displaced shapes of this particular frame. Now if these are as I have explained in terms of direction and story, suppose these are numerical values. if these are numerical values, suppose n1, n2, n3. This is also n1, n2, n3, like this. These are the numerical values. Now, from the numerical values, how you can understand that in which direction this particular frame is, or this particular point is displacing. If these are numerical values, obviously the displacements will be in numerical values, right? Something mm, centimeter, meter, whatever it is. So these displacements will be in numerical values. So based on what you will decide that it is in the direction of 1 or it is in the direction of 2. Or if I just draw it like this, xx, zz. So how are we gonna decide this? Now we're gonna decide this depending on the sign convention. So whenever we are getting the numerical values, you will be getting the sign convention like this. Suppose it is plus v, because in the direction of x, and minus x it is, suppose z minus z. So it will be plus v, it will be plus v. That means if all these three values are positive, you can say that this point is displaced along this direction, x direction. Now here you will find it like plus v, you will find it is minus v, you will find it is minus v, if these values are numerical values other than this kind of representation. Now here it is plus v minus negative value, again positive value. So you can easily understand how it is displacing now. So some numerical value with the sign convention will give you a proper idea how that particular point or how that particular story is displacing. Okay, so any type of frame or any type of structure, if you give an initial excitation, it will have a fundamental behavior like this. If it is a 2D frame, it will have a fundamental behavior like this. Why? Because this 2D frame have only 1 degree of freedom. Okay, every single story has 1 degree of freedom, which is in x direction. Okay, so that's why it is moving to and fro in this particular direction only. Right? Now, if you imagine a 3-dimensional structure, if you imagine a 3-dimensional structural model like this, suppose okay, so suppose it is a 3-dimensional structure. So now what you can expect from this? Now how many degrees of freedom each floor has? So if I draw one single floor, we have a degree of freedom along x direction. If I draw it like this, x, y and z. So it has a degree of freedom along x direction, which is the translational degree of freedom. That means this particular structure can translate in this direction, to and fro, right? Positive or negative. Then it has another degree of freedom in this direction, so it can translate along this direction also. So can you tell me, there is one more degree of freedom that we have for this particular plane. What is it?
Rotation.
Yeah, so we have a rotational degree of freedom. So if you see here, it will be something like this, right? It will be something like this. So rotation about z-axis. So every single story in this particular frame, or in this particular 3-dimensional frame, we have every single story with these 3 degree of freedoms, 1, 2 and 3 degree of freedoms, right? So that means we can expect every single story to behave or to translate or rotate about this axis, z axis, or to translate along x or y axis individually, right? Now what is the ideal expected behavior? The ideal expected behavior is whenever it is displacing along x direction, it will displace like this. That means the whole story, all the stories will be displacing like this. This is the ideal behavior for us. If it is displacing along y-axis, then it will be displacing like this. And if it is rotating, then all the floors will be rotating. This is the ideal or expected behavior, initial expected behavior for a three-dimensional structure. Now, obviously, it is not like that it should not, like there is, if you distribute the stiffness or mass in such a way that this particular frame is having, at the very initial stage, is having this rotational degrees of freedom active, then you may have this kind of. Now see, every single direction has their individual opportunity to, I can say, show you the behavior that we have seen in the multi-degree of freedom system in case of two-dimensional structure, right? If you just consider the x direction, so this x direction frame, this particular plane that we are talking about, it has full right to behave like this that we have just seen here in the 2D case. Again, if you see this plane, it also has total freedom to move or total freedom to behave the way we have explained here. And again, the additional one, which is the rotational one, so all these three floors have full freedom to rotate individually, right? So that means every single direction has its different displaced shapes, or it can give us different displaced shapes, right? So these displaced shapes, if you see in a single degree of freedom system, in a multi-degree of freedom system 2D, or in a multi-degree of freedom system 3-dimensional 3D, these displaced shapes are called my mode shapes. These displaced shapes are called as my mode shapes. Now what you have understood from the mode shapes, that if we give an initial excitation to the structure, this structure is behaving like this, like we have seen here, based on its degrees of freedom. So that means if your structure is subjected to any kind of lateral force, okay, any kind of lateral force in future, that structure, the initial, or you can say the fundamental behavior of the structure will be exactly same like this. Okay, maybe the displacement will be higher, the value of displacement will be higher based on your amount of force that you are applying, but the shape that you will be getting at different you can say time span when the structure is subject to the lateral forces, that shape or the displaced shapes will be similar to the shapes that we are getting subjected to the initial vibration. Okay, so these shapes we call as mode shape. Now if the structure is subjected to any lateral force, you are getting this kind of displaced shapes. These are also mode shapes. Even if it is subjected to no force, initial vibration, and suppose if you consider that there is no damping in the structure, damping means the initial, I can say, internal friction, right? So if you push a structure like this in this direction, it will not move to and fro all the time, right? Gradually it will the vibration will decrease and it will come to its rest. Why? Because it has internal friction. The whatever suppose it is concrete structure or steel structure, the materials have their internal friction, which we call damping. Okay, so damping is nothing but an external force on an external element that is dissipating the energy that we have given to the structure, right? So due to this, it will come to rest. Now suppose you consider there is no damping in the structure, so what will happen? If you give an excitation, the structure will vibrate like endlessly. There will be no end of this vibration, because there is no external element to resist this, right? So if a structure is moving like this, if after giving an initial excitation without any damping, so we call it free vibration. We call it free vibration, right? And if the vibration is subjected to some force and there is also resistance, so we call it let's not talk about resistance. If we give any force like lateral force, the earthquake force, wind, so in that case those vibrations are called forced vibration, right? So let's not get into all these things. So the basic understanding is, once you understand the fundamental behavior of the structure, how it is going to displace or deform under in the initial condition, then for any kind of lateral force you will prejudge, or you will judge before getting that force, that how the structure is going to behave, what is the expected behavior of the structure. Okay, so what we expect that that the structure will behave. If the force is from x direction, it will translate along x. If the force is along y direction, the translate along y, right? And if the force is diagonal or something else, or if the you can say distribution of, you can say, stiffness is in a different way, so we may have a rotational degree of freedom. So these three things are expected behaviors of the structure. Okay, now every single direction, x and y, will have these three behaviors that we have seen in the multi-degree of freedom system here: 1, 2 and 3. So you can divide the modal shapes as a whole for the whole system. So in that case we will assess x, y and z together, and we can also break it for each direction, which is these directions we call it plan direction, because these are the plan view and we have x and y here. So we call these as x and y. So we call these directions as plan directions. Okay, so now this analysis of displaced shapes based on the mass. Now why we are talking about mass? Because let's talk about the earthquake force. So the earthquake load, it's not a actual load, right? The earthquake load is not an actual load. So the vibration, or you can say the not vibration, it's a ground motion. So the ground motion or acceleration that we are getting in the ground, so due to this we are getting some inertial forces in the story levels. So as it is inertial force or inertial load, so obviously it will be acting on the center of mass of the structure. Okay, center of mass of the structure. Again, as we have already assumed that, so this is one concept, and again we have assumed that the total mass of the story is concentrated at one particular point, and we are considering these structures as multi-degree of freedom systems like this with lumped mass. So obviously the forces will be acting on the center of mass itself, right? So here this analysis of different mode shapes or understanding its fundamental behavior is what our topic is: modal analysis. Now if you see, this whole thing is based on our mass. So that means to create this kind of you can say displaced shapes, if it is a massless body, it is not possible, obviously, right? So there is some participation of mass here to have this particular you can say shapes, because the mass is actually displacing. The mass is actually displacing. So now this direction. Now at what extent this mass is participating in order to create this kind of displaced shapes or mode shapes, that also we can find. Okay, so one more thing, as we have given some you can say initial vibration to the structure. So obviously the structure will be oscillating like this. So as it is it is vibrating or oscillating, so we will have time period of it, right? An oscillatory body, so it will have a time period to complete one oscillation. We call it time period. So suppose we get this particular shape at time period t1. We get this display shape at time period t2 and this display shape as time period t3. In case of 2D multi-degree of freedom system. In case of 3D, suppose this is t1, at t2 we got this, at t3. Now see, here I am talking about the whole structure. Obviously I can break it into two plane directions, and I can give it t1, t2, t3, and as a whole I am defining as t1, t2, t3. It will be completely different. You will see that if I assess it only for one direction, this one direction, one directional behavior will be having its separate time periods, and as a whole it will be having separate time periods. So if you see the software programs, whenever you are creating a three-dimensional model, it assess the structure as a whole. So all the three direction it will check, and it will give you the results like mode 1, like mode shape 1, mode shape 2, based on its time period. So higher time period, mode shape 1, the less than this, mode shape 2, less than this, mode shape 3, like this. Okay, so but again we need to have individual behavior also for the each plane directions, because in our code it is mentioned that we need to assess the structure for each plane directions also. Okay, so that's why I have explained this particular thing first, and then I have went into the three-dimensional behavior. Now, as I was saying, that this mass will have some participation in I can say having this particular I can say mode shapes. Okay, so how much extent, at what extent the mass is participating, or this mass is being used, so that we can find out using a very simple formula. Most probably it is summation of mj phi I divided by summation of mj phi I square. So it will be something like this. This is the mass participation. Okay, so it will be mj, that is, suppose I will write it here, m1 phi 11 plus m2 phi 21 plus m3 phi 31 divided by similarly m1 phi 11 square plus m2 phi 21 square plus m3 phi 31 square. So these things, these explanations, you will find it in, as I said, in AK Chopra. So this is my mass participation, that what amount of mass is being used to get the, so here I have explained about the step 1, which is my mode 1. To get the mode shape 1, what extent of mass is being used. So this is called the mass participation. This is called the mass participation for the modal, I can say mode shape. And these display shapes that you are getting, phi 11, phi 21, phi 31, these display shapes, or you can say this displacement values, not the display shape, this displacement values we call it as eigenvector. If you are solving it using the eigen method, so it is the eigenvalues. We got the eigenvalues, and if you put these eigenvalues into one single matrix, that matrix will define the total behavior of the structure. So if you put this phi 11, phi 21, phi 31 in one single matrix like this, and if you define it with one particular variable, so that variable will give you the complete behavior of the structure. So now you can combine all these, you can say, values in one single matrix, and it will give you the, this is called the modal matrix, and we call it this, the variable which is defining the total behavior of the structure, it is called the eigenvector. Okay, so now there is a one more concept, which is a Reed's analysis. That means here we have given an initial vibration, there is no external force acting, or no, you can say, other than the initial vibration, there is no other external force like earthquake or wind or something. But if you want to, especially this modal analysis is being used for the earthquake analysis, because the inertial due to the inertial forces will be having this kind of behavior. In case of wind, it is direct force, so we know how it is going to displace, right? So most of the cases, this is a concept of seismic analysis where you use the modal analysis. But rather than this, at the very beginning, when you are going to start the framing or structural modeling, what we do, after completing the modeling, we should analyze the structure, or we should check the you can say modal shapes, how it is behaving for suppose no load, only for dead load you can check, and then based on this you can decide your framing, how you should you can say distribute the stiffness and mass like this. Okay, so that I will show you in a while. Now what I was saying, there is a reeds analysis also, where you can see this kind of behavior subjected to some specific force or acceleration. Okay, subjected to some specific force or acceleration. Same concept, just the analysis method is different. Here we are considering that we have initial vibration and that the structure is moving freely, and for free vibration we can say. But in reeds analysis, there will be a particular acceleration or a force for which will be I can say assessing the structure or structural behavior. Okay, so that you can see in the software, I will show you. And again, if you want to, as I was saying, I will say for everyone, if you want to know about the theoretical or mathematical formulation of this modal analysis, you can always refer the book of Dr. A.K. Chopra. This is the best book for this. Okay, Dr. A.K. Chopra for dynamics of structure. Okay, this is the best book for this, and you can refer other books also as well. Fine. So now so we understood how the modal analysis is being done, right? Now if I just jump into the software, because finally we are going to do it in the software. It is not possible for one single frame. You may find out the matrix and even you may see how it is behaving, but for a three-dimensional structure it is very hard for one to find it manually, right? So now we have this G plus 1 2 3 G plus 3 story structure, and what we are going to see how this structure is behaving. Now it is very pretty simple structure. If you see in the plan view, it is a very simple structure, right? So obviously we will not have any absurd behavior. We are not expecting some absurd behavior here. So as a whole, if we say that we expect that this structure will displace along x, it will displace along y, and it will have rotational behavior. So it is called u1, u2 and u theta. These are the fundamental behaviors as a whole. Okay, so now if we just see the definition of modal analysis here, define load cases and modal. You can see here one thing. So I have given the name as modal. Here you can see we have eigen or reeds vector. So remember, to understand if your structure is correct or if your structure has any you can say defaults while modeling it, it is always better to run the analysis with eigen. Even though you know the advanced process of applying the reeds analysis, it is always you can say suggested to run the modal analysis with eigenvector first, because the eigenvector, what it does, if I say in general, what it does, it checks the model as a whole. Okay, it checks the model as a whole. So wherever there is any you can say local vibration, suppose by mistake you have not connected this beam to the column by mistake, and it is not visible also in the model. So what it will do, it will not understand this local behavior, because this beam will vibrate locally, right? So it will not understand this local behavior, and it will show you that somewhere the mass is not participating, because if you include the whole mass, the beam mass of this particular beam is also included here in the M1. So somewhere you will see that there is a lacking of participation of mass. So from there you will understand that somewhere we have a local vibration and we have to correct it. And then you can go for the reads analysis. Now what reads does, you have a structural model and you have a small antenna. This the same explanation you will find it in the YouTube also by the founder of, I can say, CSI, the Mr. Ashraf, that he only explained the thing, right? I think most of you have seen that what reads does, and the same thing is also written in the help, you can say, documentation of ETABS. If you open the help, you will find the documentation. So what reads does, reads also captures the local vibration behavior. So if this beam is behaving like this, it will not say that it is wrong. It will say, okay, it is correct and I will consider this vibration. Okay, so to have a precise, but why is it the wrong process? No, actually why it is being I can say applied here, that if you have a structural model with a bigger component and with a smaller component on it or anywhere in this, so to get the actual behavior of these smaller components also, including the bigger component, then we need to go for the reads analysis. That's why you will see that most of the structural engineers you can say recommend that keep the structural model as simple as possible. Do not model everything there, right? If you compare the behavior of this small element here with the whole structure, suppose it is a building of 10 story and there is a small you can say antenna or small pipe or small tower on it, how you can compare the behavior of this small structure and this small pipe? It is not possible, right? Or it is not correct that if we compare this behavior. So in that case, we need to understand the individual behavior of these elements and the individual of the behavior of the structure, right? So in this case, reads analysis is more competent. Okay, so today we will not discuss that much. We will see the eigenvector analysis. Now, what is the number of mode shapes expected? Can anyone tell me? What we have already explained, that every single story is allowed to move in its 3 degrees of freedom. Now we have how many stories here? If you see, 1, 2, 3, 4, 5. 5 levels we have. So every single level is allowed to move in these 3 degrees of freedom. So how many numbers of mode shapes we are expecting? So this is 15, right? So it is 15. That's why I have written it as 15. Okay. So now number of minimum modes. So obviously at least one number of mode we expect. Now this frequency shift and cutoff frequency is not useful when you are doing the seismic analysis, because this is the limit that you can set. Then what is the lowest limit of frequency from where it should analyze, and what is the highest limit of frequency that we should analyze. Lowest limit we always keep it 0, because we also understand if there is any element which is very stiff, in that case the time period will be less. Okay, so frequency will be what? Frequency will be higher. So to understand all these behaviors, if you see, we have a response spectrum curve like this, right? For the static analysis we have like this. Why? Because in the static analysis we are considering only one time period, and for this time period we are finding out the acceleration. But in the dynamic analysis, see, in the static analysis, now if we give this handle, what will happen? We may end up considering a lower value of acceleration, right? So we do not want this, because the structure will not behave like this. That's why in dynamic case, why we are considering this particular thing, because even though we are getting this lower frequencies or lower acceleration values, ultimately we are going to combine all these responses and we get one resultant response, right? So that's why that it is not an issue for the dynamic analysis. But for the static analysis, we always want to be in the conservative side. So that's why we are not considering this. So these things are the seismic analysis aspects. So I am not going to say this now. So these two things are not that much useful now for us. Convergence of tolerance, it is also related to the frequency shift, and allow auto frequency shifting, it is also you can say subjected to this frequency shift. So all these 3 options we will keep it as it is, Okay, if you understand this, it is given in the help test, help and documentation. You will read about it, but these are not useful for our daily practice. Okay, so now I'll click on OK. I'll click on OK. It's already analyzed actually. Let me analyze it again. So what is the expected behavior? The structure will move along X and along Y and about Z axis at the very initial cases, right? So I'll go to my show deform shape here. I'll go to mode. So here we have got mode number 1, and if I click on apply, so are we getting the expected behavior? The structure is moving along X direction. Now if I just see here, now this mode shape, what is the time period for this? It is the 0.819 for something. We are getting this time period. Now if I see the next mode, what will be the next mode? Expected next mode, Y direction. So if I just, you can see here, and if you see the third mode, it will be rotation about Z axis. Are we getting the rotation? If you see from the plan view, right? So now see, some of you may say that is it compulsory to have the first mode in the X direction? Can't it be in Y direction? Obviously it can be in Y direction. So what we expect, that first two modes will be translatory along any planned direction, or translational along any planned direction. This is the expected behavior. Now based on how the stiffness, suppose the stiffness is very high along the X direction, so what will happen? The first mode will be along Y direction and second mode will be along the X direction. Okay, so based on your distribution of stiffness, it can change, interchange the planned directions, but we do not expect the rotational behavior at the very first case itself, because in that case what will happen? When the structure is subjected to some lateral force, suppose from this direction, the structure at the very first case, the structure will rotate like this. So obviously when the structure is rotating, the force concentration on these elements will be higher, right, which is not a desirable condition. So that's why the even in the code you will see that it has says the first two modes should be translational and the third mode should, that means it is asking you to have the very fundamental behavior for the structure. Doesn't matter whether it is a circular shape or whatever shape it is, but considering the structure as a three-dimensional multi-degree of freedom system, whatever we are expecting from that as a fundamental behavior, it should reflect in your structural model also. Okay, so now how you can understand the rotation? So you will see also there is an option called draw contour shape, contour objects, and I will go to displacement resultant, and again I will go back to the first mode. I'll click on apply. So you can see now how it is displacing. 3D view I'll go. So what is this blue color? This blue color is showing us the maximum displacement. So obviously we expect the maximum displacement at the top. For the second mode, Y direction, and at the top we are having the maximum displacement. Now this contour will help you to understand the rotation actually. So I'll go to the third mode. Now you can see the rotation. So it is rotating, keeping this particular thing in center. So what does this mean? What does this mean? That means the center of rigidity, we consider that the center of mass is here. So the center of rigidity also coinciding with the center of mass somewhere here. Okay. So now if I just make a simple change in it, suppose what I have done, suppose I have drawn a small shear wall here, okay, for whole story, fine, and now I run the analysis. Now what do you expect? Do you expect the same behavior? Let's see how it is behaving. I will go to the plan view of top story. and I'll see the first mode. Mode 1 and apply. The first mode is okay. Why the first mode is okay? Because we have given the shear wall in this. So shear wall is always weak in the outer plane direction, right? Now let us check the second mode. So we expect the second mode to be in translational along y direction. So if I just click the second mode, but it is not translating. Now you can see we are seeing that the second mode is rotational. Why it is rotational? Because if you see, we have higher stiffness here, right? Let me go to the undeformed shape. Now we have higher stiffness here. So previously the center of mass and center of stiffness or center of rigidity was coinciding here. Now as we have increased the stiffness here, so obviously the stiffness will be shifting towards this. So suppose the center of stiffness is somewhere here now. The distance between this center of mass and center of stiffness, this is the eccentricity. So what will happen? Now suppose I have grabbed this area firmly and I have applied the load. The load will be applied on the center of mass somewhere here. I have grabbed this zone here. So obviously this zone will try to resist the force, and as this zone is having less stiffness, so it will translate. So it is not translating or translating less, it is translating higher. So obviously we will have a rotational behavior like this, right? This is what we got in the you can say analysis result also, right? So it is showing in this direction. Actually it is okay, same thing like this. Okay, so how this contour value is helping you? This contour value is giving you the displacement shape values. So the blue is the highest displacement, the magenta is the lowest displacement, right? So that means this particular corners are displacing higher compared to this. So that means the concentration of rigidity is higher here compared to this. Now what you have to do, what is the measure? You have to increase the rigidity in this direction, right? This is the measure. Now you can do that, like I have just assigned it shear wall just to explain you. It can happen due to the column orientation also. Suppose all these columns are oriented like this, and here all these columns are oriented like this. So what will happen? This particular direction has more rigidity and this particular phase has less rigidity, because the column dimension or orientation we have changed, right? If you see, the higher dimension means higher rigidity. So in this case also you may have the rotational behavior. You have to check actually, right? As a whole, the distribution of stiffness and mass will affect your modal behavior, and understanding that from the contour you can assign your you can say frames or shear walls wherever it is required to control that rotation, right? So now if I show you one more thing that I was talking about, which is mass participation. We are almost at the end of this session actually, so just one last thing that I will be explaining. Okay, let me analyze it. So by seeing the mass participation values also, you can easily understand how the structure is behaving. Okay, so if I go to tables, analysis results, structure output, modal participating mass ratios. So here is the table. So we have 15 modes. Now at the very first mode, the mass participation is higher at what direction? If you see, we have ux, uy, uz, rx, ry, rz. Okay, individual directions, translational and rotational. So our concern is these two and the rotational, because we have 3 degrees of freedom, x, y, and rotation about z, right? So for the first mode, the mass participation is 83% for the ux direction, that means x direction. So what do you understand from this? That the total structure is moving along which direction? X direction. If you see here, there is no other participation in the you can say y and z. So it is ideally moving in the x direction. For the second mode, it is ideally moving along the y direction. For the third mode, it is ideally rotating about, where it is rotating about my z axis, the third degree of freedom. So it is the as a whole behavior. Now if I see the individual behaviors, individual directional behaviors, so here mass is participating along x direction, mass is participating along x direction, mass is participating along x direction. So it is the first mode of x direction, it is the first mode of y x direction, second mode of x direction, it is the third mode of x direction. Okay, and in the third mode you will have some rotational component also, something like this we see. Okay, I think in the this one also we have the some rotational component. That is not an issue, but the maximum mass participation we are getting here. Right or wrong? I think, let me check. Yes. Now for the y direction, first mass participation, second mass participation, third mass participation. So this is 1, 2 and 3 for uy, y direction modes. So the expected behavior, what you have to do, the code says for each planned direction, x and y, the first two modes should be translational. You have to check for the each planned direction, and the summation of first three modes, it should be 65% mass participation. So if you see 83% already we have got in the first mode, so we do not have to worry about it. Here 83% we have already got in the first mode itself, in the y direction, so we do not have to worry about it. And as a whole, if we check, the code says that the first mode, second mode should be translational, and the third mode, it can be rotational. There is no mention actually. It says the first two modes should be translational as a whole for the whole structure. So obviously first mode is translational along x direction, second mode is translational along y direction. So it is correct. And again the code says that at the very end, like suppose you have considered 15 modes, the 15th mode should have at least 90% of mass participation. That means F, M1, M2, M3, these masses are participating here in creation of this mode shapes, right? So what we expect to understand the whole behavior of the structure, combining these all modes, mode 1, 2 and 3. So here we understood the complete behavior of the frame. Okay, so 90% mass participation means you have covered most of the behaviors. Obviously there will be some lacking, there will be some dissipation, or you can say not dissipation, there will be some mass which will not be participating maybe, but the maximum behavior you have considered in your structure, or you have checked in your structure. Why it is very important? Because whenever you are going to do the you can say response spectrum analysis, these behaviors or these directional behaviors will be actually used in the response spectrum. So there you will provide some acceleration, and that acceleration will behave, or will be, you can say, multiplied with the behavior that we are getting in the modal analysis, and then we will be having the response spectrum, you can say response, the structural response. Okay, so that is a different topic. We may take another session about it in detail. So that's why this modal analysis is very important, both for the initial understanding of your structural behavior and also when you are doing the you can say response spectrum analysis. That means dynamic analysis of the structure. Okay, so here you can see summation of all the modes, mass participation is 95%. For summation of all the modes, mass participation is 95% for each plane direction x and y. So it is correct. There are some people, there are some engineers who say that mass participation is first three modes. So they consider the first three modes as this, as a whole. And they say that for the first three modes, it is more than 65% here. But it is not correct at all. If you see the code, it is clearly written that first three modes in each plane direction. Okay, it is clearly written that first three modes in each plane direction. I may show you. This is the last thing that I will be showing you now. So where it is? Yes. So if I show the modal analysis table number 6, right, where we have the irregularities. Table 3, table 6, yeah, here. The first three modes together contribute at least 65% participation in each principal plane direction. The same thing is also written here also. At least 65% mass participation factor in each plane direction. So do read this thing also. Okay, do not read only the first three modes. First three modes in each principal plane direction. That means x and y. Okay, so you have to find out the mode shapes of each plane direction. 1, 2, 3, 1, 2, 3. You add it up, and if it is 65%, it is okay. Now for this regular structures, it is very simple. At the very first mode, you will find you will say that the most of your mass is participating. So here itself, you got the 83%. So there is no need of checking the other two also, right? But the concept that you have, or most of the people have, that the first three modes, you can say mentioned here in the code, is these three modes. It is not at all correct. These behaviors are as a whole, x, y, and about z. Considering the whole behavior, they have given the modal mode shapes based on the higher to lower time periods, right? So the higher time periods is kept at the top, the lower time period is kept at the bottom. So if anyone asks you what is the time period for the second mode in x direction, so this is the time period for second mode in x direction. This is the time period in third mode in x direction. Okay, so this each plane direction concept is very important when you are checking. These simple structures, you will not that much cause, it will not cause any issue. But when you are going for complex shapes, you can say complex structural, you can say elements, or you can say complex structural framing. So in that case, you may have to check these things very precisely. Okay, so I hope this mass participation concept, the modal analysis concept, is pretty clear. So obviously, I have not explained the thing in terms of theoretical, like how you will be solving it out by hand. I have not explained this thing, but as a practicing engineer, how it will be useful for you. Now you understood that it will help you to, you can say, rearrange your framing. It will understand. It will make you understand how your structure is behaving at the very initial stage, right? So now doing this at the very initial stage, obviously remember one thing: whenever you are analyzing the structure for modal analysis, the mass you have to define in ETABS, actually mass source. So what mass source we have considered? The mass source we have considered as per the seismic mass. Okay, 100% of dead load and 25% or 50% of live load based on its extent of loading. Okay, so we have, because most of the cases this modal analysis is going to be used in the seismic analysis of the structure. Okay, so we have considered the mass as the seismic mass of the structure. Okay, obviously you are allowed to check for the only dead load, you are allowed to check for the only live load, that is also possible, but initially we do that actually. Okay, so I think we have covered all the thing today. Any question, if anyone have, you can ask me now. Anyone have any question on? Yes.
A question,
Just
a simple discussion.
just 1 second. 1 second. Give me 1 second. Yes, tell me. Hello.
Just a minute, sir. Just a minute.
Yes, yes.
What I want to discuss that, as you told us that while while doing the initial modeling with dead loads only, we can check this modal mass participation.
Exactly.
100% correct.
Yes.
But as per experience, what I have observed that
Yes.
suppose we have set the performance of the building,
Yes.
of any of the building.
Yes.
Later, some loads are changed. Suppose there is an increment.
Yes.
So after doing that, what I've seen that there's the performance is compromised.
Yes, obviously, na. Obviously, what I have said, you are allowed to do that with the dead load also. But see, suppose in your structure there are some live load which is particularly concentrated to this area.
Okay.
Suppose I am going to the plan view. So you have some live load which is particularly concentrated to this area, this zone,
Okay.
compared to the other zone. So obviously, as the mass live load, what is it? Ultimately, we are going to get it as a mass, right? So as the mass is increased in this particular zone, so again this mass will cause some rotational behavior for us, because the center of mass is going to shift in this direction now.
Yes.
Right. So what I said, initially when you are modeling it, you first check with the dead load, then you decide the framing, then you apply the live loads, and also you can check with. Now if you think that obviously that we have some live load which is particularly concentrated to some corner or some direction of the building, in that case it is always better to you can say consider the live load and dead load, and then you analyze the structure, as we have done actually. If you see in the mass source, what we have done, we have already considered dead load and live load. Okay, so this is the actual thing you should do, unless or until, like what I am saying, in general buildings we hardly have any such concentration, like in
this particular, like this model, we don't have any such problem.
Yes, any such problem. That's why you can do that here for the dead load itself.
Okay.
Yes.
You are talking about very simple structure.
Yes, very simple structure I was saying. Yes. So when you are doing some complex like apartment buildings or some you can say non-planned buildings, you may have some generator and all these vibratory machines. So obviously in that case you have to consider the load of those things also during the model.
Thank you.
Yes.
One more thing, I mean, I haven't observed any clause in the code.
Yes.
Like what should be the difference? Ideally, what should be the difference between the center of rigidity and the center of mass?
No, there is yeah. Yes, I'm saying it, telling you there is no such I can say clause that is telling you what is the expected eccentricity that we should consider, but there is a clause which says if there is any eccentricity, then that eccentricity should be taken as like the torsion due to the eccentricity that will be coming. It needs to be considered in the analysis. So if you see here, let me check in which page it is. Like the static and design eccentricity, it says actually. Let me check where it is. Yeah, here. So the code is not mentioning any you can say expected eccentricity or any limitation in the eccentricity. There might be eccentricity available there in the model, but if the eccentricity is there, you must consider this. Okay, this design eccentricity need to be considered. Now again, this design eccentricity is applicable in case of the static analysis in this software. Okay, but in case of dynamic analysis, we are already you can say evaluating the dynamic you can say response of the structure. So there is no requirement of assigning the eccentricity and all. Whatever eccentricity is there, yes, like see, in dynamic analysis, in static analysis, what we do, we expect the structure behave like this. In dynamic analysis, it can be like this, it can be like this, it can be like this. So based on the mode shapes we are considering, right? So even there is any eccentricity of load or stiffness here in the structure, it will be already covered in the modal analysis, and it will be assigned in the response spectrum also, right? So there is no requirement of assigning any eccentricity again and check it for that, right? Okay. Okay. So anyone have any other question? Okay, so let me share the link of attendance today. So again, I'm telling all of you, whoever is joining the meetings and whoever is filling the, I can say, attendance forms, the certificates will be provided only to those people have. There are 147 people who have registered for the program, and we are getting hardly 20 to 30 people at maybe. So only the certificates will be distributed only to those who have joined and who have, I can say, written their names or have attended the program and given their attendance in the in our Excel sheets, right? Otherwise, we cannot provide certificate to all the 147 persons. If you're watching it later, and if you ask me that I have registered and I have not received the participation certificate, then I'm sorry for that. If you're joining, then only it is possible for us to send you. Okay. So I think we will end our session now in this. Before ending our session, I just those who have joined today, the new persons, I have already explained this later also, previously also. So those who have joined today, we have two platforms for knowledge sharing. One is our YouTube, all of you know. This is our YouTube channel where we have more than 100 videos explaining the different aspects of structural design of specifically buildings. And we have an Android and iOS based application where you will be finding different online courses on structural design and you can say site engineering, on drafting of building plans. So you can have a look on it. If you think that contents will be helpful, you can enroll for this. Again, it is totally your choice. Otherwise, our platform YouTube is always available for all of you and for knowledge sharing. And what we expect that you comment on our videos, your views, your opinions, so that we can improvise our contents in future. Okay, so thank you. That's it. I think we will end our session if you're done with your attendance today. I hope all of you are okay. Let me share the link in YouTube also, those who are joining from YouTube. Yeah, there is a question on YouTube. What it is, while checking for torsional irregularity, spec X, only X displacement to be noticed for both X and Y to be considered for spec X. I didn't get what you are saying actually. Torsional irregularity for spec X, only X displacement. Yeah, torsional, if you are seeing for the spec X direction, that means X direction force, then obviously you will check the X direction displacement only, na? You will be having displacement along X direction only. That is what you need to check. See, if you are combining modal analysis and torsional irregularity together, then it will be very different. Don't confuse, okay? How to check for dual system as per IS1. What you want to check, engineering guys? Please let me know what you want to check. I'm reading the comments from the YouTube actually. Let me show you also, those who have joined from Google Meet. So here you can see the comments. So you are getting these comments where what we have a coupled mode. So if you have a coupled mode, you need to go for the code says that the coupled modes are not expected. Okay, now in some cases, if it is not possible for you to, like, there are some restraints, architectural restraints, your restraint from the client. So if there is any such condition where you have coupled mode, so that will affect the overall behavior of a structure, right? So it's not like you cannot design a structure with coupled mode. Okay, so in that case you have to analyze the structure dynamically, that means for the dynamic load cases, and then you have to design the structure, because whenever you are doing the dynamic analysis, it is considering all possible behaviors. Okay, as we are taking it from the mode shape itself, right? So it is considering all possible behaviors, and it is designing the structure. It is giving you the output in terms of the forces. So what will happen in case of coupled mode? There will be concentration of forces in some elements, there will be no forces in some elements. So where there is higher concentration of forces in some columns or beams, so obviously you have to design it for higher like forces. So those maybe the section sizes will be higher, reinforcement amount will be higher. So that's why it is not expected to have couple mode or you can say any such absurd condition. Otherwise it's not like you cannot design, it's not like the building will fail, no, but you have to consider the behavior of the couple mode in the design and analysis. That is what actually even our code also recommend. Okay, you will see all the irregularities we have. The final suggestion is to go for dynamic analysis. So dynamic analysis is not the suggestion, or sorry, not the solution. When you have no other way to resolve the you can say the behavior or irregularity in the structure, then you should consider that irregularity in the analysis, and whatever force distribution you are getting it throughout the structure, including that you need to design. Okay, but if the first mode is coupled, can the code criteria be said to be satisfied? No, the code is saying first mode is should not be coupled or should not be rotational, so you have to solve it out anyhow. Okay, you have to solve it anyhow. If there is any, see, this is not, I should not say legally, but if you are sending the structure for waiting or all these things, then all the provisions given in the code need to be, you can say, resolved. Is it always necessary to limit the frequency 33 Hz while mass participation is above 90% like for regular? See, as the code says that the frequency should be considered up to 33 Hz, because see, this concept, actually we are not going into these things today because it is a very different concept. This is the response spectrum curve. Suppose here we are having lower frequencies, here we are having lower frequencies. Okay, so means the lower acceleration values. So the time period goes on increasing. What will happen? The frequency is going on decreasing, right? So why it has says that 33 Hz, because if let's not talk about 33 Hz and all, just understand this from in general. You have already considered the expected higher frequencies here, you have considered some lower frequencies also. Now if you consider those other lower frequencies also, this is useless, right? This is useless. Okay, the 90% means you already considered all the expected behavior of the structure in the modal analysis. So after taking all these lower frequencies, what is the point on it? So that's why it says it is limited to 33 Hz. Okay, so this thing is very different concept. We may have a different, you can say, session for this. Yes, hi Abu. Any other question? So okay, I was taking one question, how to check dual system in 1893. I didn't get your question actually, how to check dual system in as per IS 1893. Dual system is just a structural arrangement. Okay, to the structural, you can say, lateral load resisting arrangement. That is what dual system is. How to check means the fundamental behavior will be same for all.
I think he's asking for 25% column.
Oh, okay. 25% base shear in the columns and shear walls. Okay. That is again a different topic. Let's not dig into it. It's not a big deal actually. You have shear walls, you have columns like this. Okay, you have base shear in these points, the base reactions, suppose A, B, C, D, here A, B, C, D, here A, B. You add up all this, or you just get a base shear value, something A. Okay, you get some base reaction here, you get some base reaction here, here, and all these shear walls. So what it says that, what is the definition of dual system given in the code? Anyone please depict it? I think 25% base shear should be there in the column, right? Or the column should be designed for
at least 25% base shear should be taken by the
columns. Okay, so that means, see, if you given shear wall here and your 100 or more, like the maximum percentage of lateral forces are taken by your shear wall only, that means your columns are acting as a gravity column. So that means these are taking only gravity loads. Okay, so these columns are not effective for the lateral force resisting. So in that case, you can call this structure as a what it was, structural wall system, right? There is a component structural wall system. Yes. Now if at least 25% of your base shear, that means total base shear that you are getting, is resisted by those columns also, and the rest is resisted by these shear walls, so that means these columns are also taking some minimum amount of lateral force, and these needs to be designed for this minimum amount of lateral force also, other than the gravity loads. Okay, so when the structure is you can see in the structure, when the columns and the shear walls are resisting the lateral force combined or as a whole, in that case we call it as you can say dual system. So now you said how to check. You just check the base reactions that you are getting from column and shear wall. If it is higher in the column, like it is, you check what is the total base shear resisted by these columns, and if you compare with the total base shear, then you can get the percentage. If it is more than 25%, you can design it for lateral forces, considering the system as a dual system. Now you may say that in the ETABS, if we model the shear wall, most of the lateral force is being concentrated on the shear walls itself, right? So in that case, what you have to do, you may have to design the columns. If you want the structure, you can say structural model to be a dual system, you may have to design the columns for some higher you can say factor of safeties, or you can say higher partial safety factors, and then whatever size you get, you just assign that size in the structural model, and you check whether the column is resisting 25% of base shear or not. So this is some iteration you have to do. Actually, it's not that easy. Okay, it's some iteration you have to do, and then you have to check whether it is I can say a dual system or a structural wall system. Yeah. What if the first, okay, it is always necessary to, okay, fine. No, actually we have only 3 days workshop or 3 days boot camp, where we have covered beam design, column design, and modal analysis today. Okay, so this is the 3 days. Maybe in future we will cover some other topics also. I have holiday from my office, so in this holiday I thought of spending the time with all of you guys doing these things. Okay, local axis direction, I didn't get actually, Sam, what you wanted to ask. Actually, missing mass correction, we will take it up later. Okay, so I think we can end the session today. It's really a great session with all of you. Okay, I hope all of you have given your attendance. Did I share this to the YouTube people? Let me share it again. I think I have shared it already. So I have already shared it, the link. You can always put your attendance, and those who have attended will be given the certificate of participation for all the 3 sessions. Okay, thank you for joining with us. We will see you in the next any such sessions if we have. and stay tuned with our you can say platforms. We will discuss more such technical things with all of your support. Yeah.
Sandeep.
Yeah. Thank you so much. Okay. So I'm closing the session, and again at the very last, happy Diwali to all of you. Enjoy the festival of light, and share the knowledge. Have a good day.